So namely perception.
And most retailers, cost of goods is in there.
Talking.
Okay. So the autonomous driving system consists of three main components. So namely, we have perception, prediction, and planning. In perception, we try to see what is around. So we try to detect the objects in the surrounding. In prediction, we try to predict how the other agents, like cars or people, will kind of behave in the future. So we try to predict their motion. And planning is the holy grail of autonomous driving, where we try to safely navigate our car to see how it's going to drive. So the way we actually train those models are they are standalone models. So you have a perception teams that try to optimize the precision, and you have a prediction team that focus on optimizing the displacement error. And finally, we have a planning team that focus on the safety of the self-driving vehicle. But such disjoint training leads to severe error accumulation. So alternative to this one is end-to-end autonomous driving. So what is end-to-end actually? So you start from a multi-view camera input, and then you get something called bird's eye view. So let's dive into this, how it looks. So if you have seen any self-driving car, they will mount multiple cameras around it. So for example, here we have 6 cameras, and it's hard for the self-driving car to digest all this information at once. So what we do here is actually we take these 6 cameras and we run them through let's say CNN backbone to get the image features. Once you have those image features, you have a BEV encoder that specially temporarily combine those features to get a one top-down view known as bird's eye view. Once you get a bird's eye view, you can actually now input it to your downstream tasks, let it be perception or planning. But one thing that I want to emphasize at this point is that this bird's eye view is a high dimensional latent space. So it can be the number of channels can be, let's say, 256 or an arbitrary number. So you don't have a ground truth bird's eye view, and your performance relies on the quality of the bird's eye view. So this is a more simplified version. So if you have, let's say, these 6 cameras, you fuse them, this is how it's supposed to look like, a top-down view. And let's say the red one is your self-driving car, and then you have all other agents in the seat. So once you get the bird's eye view, you input this into the perception stack and the prediction and planning. All these tasks are now connected to each other, and we jointly optimize them to facilitate the holy grail, like the planning. And this is actually the state of the art in autonomous driving. A fact here is actually CVPR 2023. The best paper award goes to end-to-end autonomous driving paper, known as planning-oriented autonomous driving. Of course, this has increased a lot of interest in end-to-end autonomous driving, but there are still a lot of issues that are remaining in this domain. So what are they? So the first one is the lack of ground truth BEV. As I mentioned, you get the bird's eye view. This is a high dimensional latent space, and all your tests depend on it. And the long tail scenarios is another problem. You may be doing really well on some of the common objects, but when you face a rare scenario, then if your performance degrades, you face a lot of trouble. And similarly, generalization performance. You train a model in one city, then you want it to generalize to another city, but you don't want to collect all the data. And finally, now that we are in this age of foundation model, now we not only want to drive, we also want to actually know what the car is doing. We want it to reason with for us.
So I have a quick question here. So when you say we don't have the ground truth, do we mean we don't have the 3D reconstruction, or what that really means?
Yeah, so we take those 6 cameras and then we predict that bird's eye view. We just say, but this bird's eye view, how do we kind of see if it's a good or not? Then we actually put it to a downstream task, like the detection transformer. So your quality on the detection task is it's like a proxy. But but you don't have a ground truth BEV directly to me. Okay, so we had those key issues, but what are the remedies that we can think? So now we are, as mentioned, we are in the age of the foundation models, and I'm sure you're all now familiar with using those ChatGPT. Now the DeepSeek is very popular. You have DALL-E, you have the Llama, and so the way these models are, they are trained on large large amount of data on like this publicly available data, or like if some companies, they of course they have the large scale private data as well. But let's say that once we have this foundation model, we can actually adapt it to a given task. So even though this model is not necessarily trained on object recognition, we can actually adapt it via fine-tuning an object recognition task. And it has shown a remarkable performance on variety of tasks. Can we just directly apply this to our autonomous driving? Unfortunately not. So there is a lot of bottleneck here. So in autonomous driving, the decision needs to be done in milliseconds, but those models are super large. Even though you distill them, let's say from 70 billion to 7 billion, or even bring it down to 1 billion, we still have the latency issues. So now the question is, can we find a way to actually distill this foundation model into, let's say, an existing autonomous driving stack, and or can either we decouple it or find a way to do it. Another problem, as I mentioned, these models are trained on not autonomous driving data. So we need to also address the domain gap. We need to ground those models. And the hallucination is a very important problem here. If we directly use it, and for example, if the model like hallucinates and a person on a wheelchair as a motorbike, then it's not going to slow down. And then it might result in a huge accident. So the question is, how can we actually now ground those? So to address those problems, we have been working on representation alignment of foundation models so that we can actually efficiently integrate those into the, let's say, an existing end-to-end autonomous driving stack without causing additional, like those lengthy inference time. So let's start with our first work known as vision language planning. So on the top side, we have, let's say, an existing stack is an end-to-end stack that can actually run in a car. So you get this multi-view input, and then you have the bird's eye view. And as I mentioned, the problem here is the lack of ground truth data, but now we can actually leverage the power of foundation models. So how can we do this? So in the training time, we have actually access to the ground truth information because we know like what are those objects in our training data set, like their bounding box location, their flash information. So what we can do is actually, once we predict a bird's eye view, we can actually go ahead and crop those areas based on the ground truth bounding box information. So here, for example, the red one is my, let's say, self-driving car. I crop that area, get the features. I crop the green area is a truck. I crop it. The lane segment, I know it. I crop it, and I get those features that I have predicted. But these are not the ground truth. So how can I now actually bring some foundation model? So as we are in the training time, we can actually construct a ground truth language. I can construct the following templates. The agent is like a class name. Can be a truck, can be a person, and I also know it's 3D bounding box. And I can add more information to this based on my task. If it's a prediction task, I will add some future trajectory and all those things. Now that this is the ground truth information, I can run it through a vision language model and get my respective agent-wise text features. And then now I have my textual features. I have my visual features. If you are familiar with the clip, we can actually now do some alignment, contrastive learning, try to pull together the positive pairs and push away the negative one. And this way, I can try to learn a better representation for my BV encoder. And I can do the same thing for my planner as well. Let's say that my planning is now, it's a different thing, right? So on the planning phase, I can construct a new language here. So for example, the ego car is, I know that it's turning left because I'm in the training time, and I also know where it's supposed to be. And this is the plan 3 time step, like future trajectory, XY coordinates I inputted. And now I can get these text features and then align it with my predicted futures. So I'm bringing additional supervision, a ground truth supervision here. And in the test time, right? So I did this in the training time. In the test time, I don't need this actually foundation models anymore. I can decouple it so that I don't suffer from, its drawbacks, like those lengthy inference time and those possible hallucination issues. And I will end up with a driving stack where hardware or like the system didn't change at all. Only the parameters are updated, but updated with the distillation of foundation models. So it's a training only method with no additional cost in runtime. But let's see actually how it performs. So as I mentioned, this UniAD was the CVPR best paper award from 2023. This is actually a vision only work. And when we compare with this one, in terms of those planning metrics, actually we beat the UniAD by 48%. We bring down the collision rate, which is one of the main metric for the planning. And subsequently, there was another work called VAD, which is more compact than the UniAD. We also beat that actually by 60%. And the beauty of our approach is you can actually take it and plug into any of those methods and enhance their performance. And as I mentioned, we also talk about the generalization. And then we know that those foundation models have those strong capabilities. And so here's an example where you train your data on, let's say, a US city like Boston, which has the right side drive. And in the test time, you don't have that much data in, let's say, Singapore, you want to actually deploy, which has actually different country, different driving style. And of course, we're going to check the collision rate again. So what you have, let's say, the VAD that is running in the car versus what that is enhanced with ours, we actually improve its collision rate by 50% reduction in the collision rate. And these are like the improvement that come with no extra like trade-off. And another very important problem here is the long tail scenarios. I'm not sure if you guys are familiar with this. The Cruise was a self-driving car company, and their I think in the summer the DMV suspended their license because of a long tail accident. And eventually, actually, that became their downfall. So the company like lost its backup from those major car companies, and it had to be shut down. And so this actually showed that the long tail are very important. So as I mentioned, so here, for example, you look at a person on a wheelchair, and if you mistaken this person for a motorbike, your car is not going to slow down. It has to know how to slow down. It has to recognize those objects that are very critical. These are actually the bottlenecks in autonomous driving. So we did actually some like average precision on the rare object, and compared to those models, again, we were able to get this benefit of like additional 16% improvement with no extra cost. Okay, so I have shown how we can use vision language model to improve an autonomous driving stack. Yeah.
So how do you do the testing? Assuming you're not having real car driving.
Yeah, so
you just do simulation, emulation?
Yeah, that's a great question. So those experiments are based on the publicly available data set called MuSense, and it's like an open loop testing.
So you basically, that's the
we do the public benchmarking. Yeah.
Also, I have a question about the performance improvement. You talk about the average precision, right?
Yes.
And I suppose you use that because the data is very, very imbalanced, right? Because it's long tail.
Yeah.
So what's the imbalance ratio looks like? Because this number itself doesn't tell anything, I think, because we know that the imbalance ratio is high.
Yeah.
This number tends to be very low. So
so I think this is a great question. So when we look at the data set, so for example, those rare classes are the one that exist like 1 to 2% in the data.
1 to 2%.
1 to 2. So these metrics like represent that those classes that have only 1 to 2%.
Mm-hmm.
So the other cases, like say, I mean, like the common cars are like they actually constitute like 43% of the data set. They are like the frequent ones, but we focus on the ones that are only like 1 to 2%.
Okay.
Yeah. Is there any other question? Or I will be continuing with the diffusion model. Okay. So we have shown actually how we can leverage those vision language models. So there we focus on like an agent-wise, like bringing like the ground truth information. But we want to actually take a deeper look into this problem, like with now that we have those technology with those diffusion models. So this is the setup that I have been talking about. So let's take again a closer look at the bird's eye view. So if you look at it, like as I mentioned, your performance truly depends on the quality of your bird's eye view, but you don't have a ground truth. This is a major problem in the domain. And another thing is that you take those multiple cameras, and then you have intrinsic noise in those cameras. You have this learning process where it also adds additional noise. So your actual estimation is noisy, even though those cameras, the images may not look noisy. If you take actually a deeper look into it, so we did some studies to see, let's say, if you take those features, let's say you have a 200 by 200 by 256 bird's eye view picture. And then we like average over the channel dimension. And this is what actually the self-driving car is actually consuming, the one on the leftmost. You can see that it's not actually very representative. So just to give you an idea, the LiDAR top view just shows you what are the objects around.
Yeah, I just have a question.
Sure.
So BEV is an actual representation of the data. So
Yes.
As you mentioned, we cannot verify its performance because there is a lack of GT.
That's correct.
So why can't we refer HD maps? Because most of the planning algorithm relies on the HD maps, high definition maps.
Mhm.
So it comes up with some static features,
Yeah.
like a signboards, whatever it is.
Yeah.
Representation of BEV
Mhm.
and these side features, which just have a static
Mhm.
location information. And
Yes.
so can we compare and estimate refer as a GT?
Yeah, I think that's a good point. But one of the main things is that like HTML, let's say we construct one, right? And tomorrow there is a construction on the side. That is not right, then we will have an issue. Like what our reference is no longer valid.
Yeah.
And that's why actually if you check the recent, like the state of the art methods, they're actually moving away from the HTML. Because you have a lot of like, those drawbacks, the environment keep changing. And this is one of the reasons they are not leveraging those HTML.
Okay, thank you.
Okay, yeah. So as I mentioned, on the right hand side, you have the LiDAR top view that shows actually how the objects are supposed to be located. And on the left hand side, you have a produced BEV that is actually, if you look at it, is noisy. Whereas on the right side, if we have it, a denoised BEV that actually imitates how the LiDAR top view looks like. So if we can get a denoised BEV, we can actually use it as a proxy to guide the whole process of that noisy one. And how can we get this one? Of course, the diffusion models are very powerful denoisers in the domain. We all know about it. They have shown remarkable performance on a variety of the tasks. And then it's also like a candidate for autonomous driving now. So we can try to denoise it with diffusion model. But I think the question will be, it's like, as I mentioned, we are trying to make the decision in milliseconds, but the diffusion models, they have those lengthy inference time. So how can I avoid this lengthy inference time for the practical purposes? So now I'll show how we can actually address this problem. Of course, this problem is has multiple stages. The first thing is that those diffusion models are also not trained on autonomous driving domain. So you don't actually have a diffusion model that is already existing for autonomous driving tasks. So the first thing that we need to do is to fine-tune those models to autonomous driving domain. So how can we do this? So what we can do is that, let's say that we have a pre-trained BEV model that doesn't, let's say, necessarily produce very good BEV, but we can start from here, take a produced BEV and add some additional noise, just the standard diffusion process. But very importantly, what we are bringing here, again, we are in the training time. So if you want to denoise, you want to go from one stage to another, you should have a guidance. Otherwise, you don't know which state you are converging to. So this is actually like our secret recipe, is that to bring that ground truth information that we already have it during the training time. And so what do we have? We have the class information, we know their bounding box information. So actually I can use this layout information and to guide my denoised BEV to a better state. So I take the produced BEV, I generate a denoised one, and then at the same time I'm attaching it to the downstream task so I can train a diffusion model for my task. So the first stage is to get this model. And the second stage is, now that I have this pre-trained model, I can actually try to now bring the supervision, because I don't want to suffer from the lengthy inference time. Otherwise, this method will be actually impractical. But I still want to make it practical. So what I can do is that on the top, again,
Previous step, so when you're training the diffusion model,
Yeah.
you have the classical denoising loss
yeah,
plus the downstream loss.
yes, that's how we do it, yeah. Okay, and then in the second stage, we will actually have, again, two-stage loss. So on the top, we have a model that is, let's say, running on the car, our BEV model. But on the bottom part, we will actually bring a supervision. This is training time. And we bring the produced BEV, so we input this to our diffusion model. And again, we have the access to the ground truth. So now I can get actually a true layer denoised BEV that I have shown in the earlier slide. I have a denoised BEV. So now I don't need to only rely on a downstream task loss. I can bring a BEV loss. That is a proxy denoised loss. So it can serve actually as my supervision loss. It's a proxy ground truth, but it shows a much better reference. So it can guide my learning process. And in the test time, again, I can decouple this model. I don't need my diffusion model, so I don't suffer from my lengthy inference time. I have a model that can actually denoise the intrinsic noise and achieve a better performance.
You're using diffusion model just to generate kind of images. I'm kind of
Yeah.
getting confused where the diffusion model come into picture. Why can't you just using, for example, earlier using the vision language model to prediction stuff? So your kind of representation, trying to get a more accurate representation, is that
Yeah.
use diffusion to kind of paint the images?
Yeah, so I want to go back to maybe this slide. So the bird's eye view, so if you, this is how it looks, it's a noisy one. And I want to bring a supervision to it, like something that can guide it to be a better, like say, a better representation. And so, which means, so if I have something noisy, I need to denoise it. So the problem is that the BV itself has a noise, and the noise needs to be removed.
So here you already talked about representation space, embedding space,
Yes.
not original image space.
Exactly.
Right? So you're
Yes.
using diffusion model to generate another kind of embedding,
Yes.
something which has.
I am
better-
using the diffusion model to take a noisy BV and
It's already
denoising it.
high dimensional representation.
Yes.
I mean, the representation.
Yes, exactly. And I'm denoising it. If I have a denoised one, which I mean, a proxy ground truth, I can use it to guide my original model.
So my question is, I think you should do denoising like real time. And diffusion models, like running diffusion models takes very long time. So how do you do it in real time?
So this is the training time. So I can train the model, but in the test time, so once you train your model, right?
But
Then
even the inference time of diffusion models is very high.
yes, that's why we are actually bringing those plugins. So you can see that I have a dash line. So this dash line means this is what is running in the car, and this is in the training time, I'm just bringing this as an additional supervision. In the test time, I am discarding this completely. I don't have this in the test time. I just improve my learned parameters using the diffusion model.
So again, evaluating the diffusion model is still challenging, right? Lack of GT, proper GT.
Yeah. You mean I didn't really get the question. Can you repeat that?
Evaluating these diffusion models.
Yeah.
Is still challenging.
Yeah, so evaluating, but we can use the public benchmarking, right? You can benchmark it compared to what you have. You have a model that is, because your trained model doesn't like your top model doesn't change, right? It's just that your learned parameters change. So how does it compare to the previous model, right? If you do the proper benchmarking, you can have an idea which one is, whether it actually halves or or it hurts, right? That's the main idea. So that's why we need benchmarking. Yeah.
So in this kind of two-step process.
Yes.
Doing the diffusion training part, so some of the parameter you can also train essentially you make the multi-view image feature kind of for that neural network model, basically you almost like encoder decoder type of thing, you can modify the one to help you better a feature that can be
exactly
features.
Yeah, the main goal is to have better parameters. So technically what really, like if I have a very good learned parameter, like a representation space, it can actually help me denoise and get a very good bird's eye. And then I can actually do the detection or any downstream comes much better. But the problem is that those parameters are not that good. We can understand that from the performance. Yeah.
So what are the downstream tasks you guys considering?
Yeah, so in this task, we are considering the perception tasks like object detection mainly. But as I've shown in the previous case, you can also take this model and then input to a plan. See how is your planning performance as well.
But I saw you already had something, part of the model, you already having the class label, which you already rely on the object detection bounding box. So you seem to have a little chicken egg problem, right? So you already had the bounding box, which you
So that's a good thing. So you have the bounding box, but that loss comes at the very end, right? Let's say you do the detection transformer after this one. Your loss is at the very end, but your main thing is at the intermediate stage, and you don't have a ground truth on it. So if you can bring represent a supervision to that one, like your main problem, then actually you can improve your performance.
So
I think he has. Go ahead.
so my question is very adjacent to what I was asking. So in the car, you have the system that is based on some heuristic to produce the VAVs.
Yeah.
And that heuristic has some hyperparameters that you need to fine tune, and you are taking the ground truth from the denoised version because you don't have the denoised version in the upper level. So you are fine tuning your first algorithm to match what the denoiser is doing. What I'm wondering is, what is this heuristic? Is a way that how can it do noiseless reproduction of the BAV from the ground truth in the first place? Like, is the compressed model that can do, like, does it work like diffusion, or is it something whole different that is inherent to BAV things? Like, what is that heuristic?
Yeah, so the idea is that, as I mentioned earlier, like the BAV inherently is not clean, right?
Right.
I've shown that it has noise in it. And then what can we use? Like you need a denoiser, right? You can maybe use other denoiser as well. But diffusion is one of the candidates. And how can we ensure that it converts to a denoised one, right? Like what if it goes to even a worse state, right? That can be the case. But we are addressing this problem, as I mentioned in the earlier stage. We still have our downstream task log. And very importantly, we are bringing guidance. Like when it denoises, we have a conditional, right? That it says that these are the ground truth objects. So denoise is based on this conditional information. So this actually helps with you actually to get into a better, like a denoise state. Otherwise, if I just don't have anything, then your question actually will be very valid. But we are bringing that ground truth guidance to guide it to a denoise state. Yeah. Sure.
How do you achieve that guidance, that condition? Is it simple like cross attention layers, like stable diffusion?
Yes, it's exactly that one.
Okay.
We are actually using the layout diffusion model to do this.
So it's like a text guidance, but with the layout objects.
Yes. Yeah.
So I know in like multimodal like learning, people actually want to like learn a kind of common features, but they still want to like keep some unique part, because they are saying like this kind of unique parts may be quite important to like for some downstream tasks. So this kind of unique feature may be kind of in some level maybe noise. So here like you are almost trying to like remove this kind of noise in the kind of latent space. So how do you view that? Because here like I'm also thinking like this kind of noise may also somehow like may provide some information for like different views, right? Yeah.
Yeah, I think this is the way we do this one is that we are like, I mean, you may learn something, right? But at the same time, we are like we are not altering your original architecture at all. You're just bringing an additional supervision to help with your learning process. Does that answer? Or maybe in the later stage, I'll show how we can also do like some for different tasks, how we can do it, then we can answer. But the main thing is that we don't change the architecture. We don't like, but we are bringing a teacher to kind of guide the student. So the top one is a student, and you have a teacher helping the student to do better. So it's like a knowledge distillation. Yeah. Okay, so yeah, so in terms of like, again, we need to do, as I mentioned, we did the benchmarking with the state-of-the-art method, see how our method performs. In terms of the detection, we show that actually in overall, we achieve a more than 13% improvement. And again, for us, what is actually more important is the rare classes. And in the rare classes, we achieved a 25% improvement compared to the baseline published in CVPR.
In this kind of example,
Yeah.
this is a still object detection.
Object detection platform.
So
yeah.
what are the example of rare classes here that you're talking about?
Yeah, so the rare classes can be, let's say, a construction vehicle, a car with a trailer.
Okay,
These are all actually long tail.
right.
Yeah.
Not like, for example, flipped car. Or
No.
something.
Yeah,
Those are the situation
these are not on the
problem.
data set, but if
Okay.
you have such data, you can actually also consider them as rare and add it into your performance benchmarking. And another thing that we consider in this case is that we train those models, but we cannot just test the daytime conditions because daytimes are much easier compared to more challenging, like a rainy day or like a night situation. And again, we show in the rainy situation, our performance improvement is actually 22%, and in the night, we even compared to the baseline, we show a 29% improvement. And I also want to show a qualitative result. So, I mean, if you are familiar with this Tesla, so Tesla, they are driving around, and it's only based on camera, so it needs to actually detect those objects accurately. So this is one of the, so this is why actually we need to make sure that our model works really well. So the teacher needs to help the student because the student is running the car. So this is the ground truth. You can see that there is a car, like a black car in the very corner. And with the baseline models, actually, they don't detect it. And if you just drive it, let's say in that location, you don't detect it, it may cause an accident. Whereas in our effort, we have shown that actually we can actually detect such situation. This is kind of as a complement to what we have shown with the quantitative metrics in terms of the rainy and then the night condition. So what are the benefits of our approach? We improve the BEV at no runtime cost. You can actually later use this as a conditional BEV simulator. So if you can just alter the layout and then create new BEVs and do more detection. Okay, and then the multimodal task alignment is the last topic of this talk. So as I mentioned in this era of foundation models, like if you get into a car, you may not be satisfied with only like the car driving. You are sitting in the back seat and wondering what is the car doing. So probably you want some explanation for the decision. So, and then of course, this is how like this autonomous cars are like they are taking this input, and now they are not only doing the detection for your cars or like plan it, but they also caption it for you, tells you like what it's doing. So for example, here we have in the like a ground truth caption that describe it. There is a white and gray truck in the intersection is moving quickly. So you have also now this information. So you are now doing two different tasks. So there is something that is running, that's trying to run the car. At the same time, you need to give feedback to the model. So let's get into the architecture. How is actually this look like? So on the top, actually, if you have two things. So you have on the top, you have an object detector. This is what I have been talking the whole talk. You get those bird's eye features. You get a detection hat, like a detection transformer. Then you have the object proposal where you then check like compare it with the ground truth information. And how do we do the captioning? We can actually use those large pre-trained models. You can use a llama. You can use any like model that you like. So, but what it does is that you have two main ingredients to this one. One of them is the textual information. So the textual information is that you are asking the question that you want. So user can actually may input even different keys. So to describe the behavior of each one of the objects. And then how it's gonna like describe it, it needs to get the visual information. You bring this information from the visual part, like those camera images, and then you input this to a relational format to make sure that each one of those predicted bugs has an understanding of the whole surrounding to get that. And then you have your visual information, you have textual information, you input to a pre-trained llama model, and it's gonna start to predict your caption. You also, because you are in the training time, now people are actually like releasing more and more data set. You can compare with the ground truth caption and then try to minimize that loss. So if you do a vanilla training, you actually have two losses, one a detection loss, one a language model involved. So this is the baseline that has been published in 2024, very recently. But what are the problems with this? So the key issue is if you look at here, there's an information flow, right, from the visual part, from like an object detector to an image captioner. But we don't care about like, I mean, there is no like an alignment mechanism that makes sure that if you do a joint training, your performance increase for both of them. You don't hurt the other. But the reality is that if you don't have any alignment, you just do like a vanilla training. The model is, one of them is gonna suffer, especially like your object detector is gonna suffer. So and then you don't want to have a model that is like having a very low performance, but just give you a caption because it may cause some accident. But you want the best of both worlds. And the question is how we can achieve this, how we can actually enforce consistency between two different tasks. And again, we are going back to the representation alignment. So we are trying to enforce two different modalities. Like you have a vision and you have a language, and make sure that these two are like understanding the same language at the end of the day. So here, let's say we are getting those features. So we have two modules here. We have those bird's eye view features. We need to make sure that because this bird's eye view feature, as I mentioned, each one of them has a visual understanding of what is around. But your caption also has a textual understanding of what is around. So these two needs to be aligned. You cannot have a visual understanding that is completely different than the textual understanding. And we can actually, again, use like a pre-trained model to run the ground truth caption to get some features and bring our visual features and just like run it through like a simple neural network to match the dimensions to make sure that our bird's eye view feature align with the linguistic understanding. And there is another thing that we need to take care of in this representation alignment. We are predicting some bounding boxes. We are doing a detection task. At the same time, we are also predicting a caption for it. And this caption also actually contains its localization information, description, all this information. So your tool has like this thing, this tool, they should also have like a joint embedding space. They cannot differ from each other completely. So how can we do this? You can either easily do it with just running them through like a multi-layer perceptron and then try to align the feature. But what we realized that if we add additional cross-model prompts that have shown impact in other domains, in other computer vision tasks, if we have shared prompts, like learnable shared prompts, and do some attention pooling, then do the alignment, then we are actually achieving a better consistency between the detection task and captioning. So then these are the results that we are showing. So the BEV form is like, if you're just doing the detection, this is a single task. If you do the vanilla multitask, if you look at the detection, actually, it actually decreases. And this is what we don't want. We want to increase the performance in both. And in our approach, like multi-model task alignment, actually show an improvement in terms of 5% on the overall and 10.7% in the rare class. And as I mentioned, we have also the captioning. In terms of captioning metrics, these are like public. We are also outperform the baseline. But I want to show like a case, how it's going to look like. So this is how it actually looks. So we have the ground truth, for example. We do the detection, but then this is the ground truth caption. For example, blue box about 19 meters away. The baseline with like the vanilla align, like vanilla multitasking, actually mistaken it as with a trash can. And also it's very off in terms of the localization. Whereas our approach actually shows a better description and also better localization. And there are, of course, some cases. These are like, for example, here, they may say blue car, we have a gray car, but we are correctly identifying the class. But in terms of the displacement, we are much more closer to the ground truth. So this is shows that, I mean, we can actually achieve both, like the best of both worlds by bringing and enforcing this alignment mechanism. Yeah, again, what are the benefits of our approach? You improve the perception at no runtime cost, so you can actually decouple it if needed, but you can also you can have a different latency requirement for both model now. And then you also have improved captioning with explainability. Yes, that is the last slide of my talk, actually, yeah. So, and this one, yeah, I want to mention that. So this is actually an important area for autonomous driving. So we are organizing a workshop on this distillation of foundation models for autonomous driving. And at the same time, as Bosch Research, we always look for AI talent. So, so if you are interested in our positions, we have QR code, and I'm very happy to take the questions now.
So is there any benchmark data set?
We'll start with the questions now.
Yeah.
Thank you, Burhan.
So is there any benchmark data set with the fusion models?
Yes, there are benchmark data sets that you can use. These are all these things that we have reported. These are actually publicly available data sets. So you can actually go and actually do the same type of experiments and see it. Yeah.
So for the last one you talk about, what is that still based on Nielsen data without the X?
This is on a data set. Well, this is called a top 3 cap data set. They actually take the nuisance data set and they caption it. So it's you can still say it's based on the nuisance, but they caption it. They are providing the captions for the nuisance.
So it sounds like most of your data set is based on using. I mean, how large is the total data set, and
Yeah,
what do you envision as to make your system truly reliable and to make that work in the real world?
yeah, of course.
Using is still emulated, it's not real world.
Yeah, that's a great question. But one of the challenge in the autonomous driving domain, nuisance is the largest public available data set. So you see any paper that are doing this type of things, they will be reporting the nuisance benchmark because that's the largest public available data set. So once and then there are maybe some now like more data sets coming, but they are not at the scale of the nuisance.
So how large is the nuisance data set you guys use for training and for testing?
You mean in terms of like it contains 1.4 million annotated bounding boxes.
Okay. So you can talk about, for example, you have a driving video, how many such a kind of video segment, because it's a bounding box itself.
Yes, so it's a 20 seconds video. They are
1
annotating. They're choosing some keyframes and they annotate those ones. Yeah.
Right.
Each one of those clicks are 20 seconds. Yeah.
On this slide, it seems like you feed the Q-former at some point. Does it matter where you take it from, from the output or some intermediate?
Yeah,
features?
actually, this is a great question. This is so one of our so this study actually has also now been done by an ICLR paper that actually received like a impressive like scores of like three of the 10s, like very high scores called a representation alignment to improve the diffusion model. What they show that actually where you do this, it matters. So you're doing at the end, you're actually not getting the best performance. So doing it actually in the middle layers is the best based on their like study. And we also actually did the same qualitative, like the quantitative study, like as an ablation, and also have the same finding. Yeah.
Any questions?
Okay, so in your diffusion guide, that project, the diffusion model by itself is fixed, right? And then you only use it to fine tune the embedding model, something like because
Yeah. In the second stage, diffusion model is fixed. Yeah. In the first stage, we are fine tuning it. So it has two stages. So the first stage is that in the first stage, so this model is now, so for example, we take a stable diffusion model, it's not actually purpose for the autonomous driving task. So we need to fine tune it. The first stage is that we're updating its parameter, this diffusion model, to ground it for autonomous driving. But once we have such a, so the reason we are doing this because we don't have such a diffusion model in our domain, in autonomous driving domain. So we are getting this by ourselves by doing like a pre-training stage. But in second stage, like as we train, this is frozen. So it's just like an inference to get that data.
and now you use the embedding vector from the diffusion model as a ground truth, and then fine tune the first model.
Exactly. I would say proxy ground truth.
And because are in the same dimension somehow.
Dimensions are 200 by 200 to 256. Depends on your BV and size, and then the number of channels you have.
Okay.
You can change it. Yeah, like you can make it like, for example, 512 if you want your BV to be number of channels higher. Yeah, and they still can align.
So I may ask a question, since you're coming from industry.
Yeah.
Working for automotive company.
Yeah.
So what do you think, what are still the gaps? Suppose since all you guys have done, would we solving all the problem for autonomous driving? What do you think are the problem issues?
Of course, this is not the solution because autonomous driving, in my view, I think it's also in the view of many of the AI scientists, is one of the hardest challenge in AI. You always have the long tail problem, as I mentioned, like the crews, they have one accident, right? That long tail accident, but that was eventually their, like, you know, that they have all those issues. So it's an area where you need to like kind of strive for excellence and then try to address all those like gaps to fully achieve like human-like driving. We are still, of course, far from it, but we are just taking some steps towards it. Yeah.
One question about this model. It
Sure.
works on multi-camera feed, like you said, but
Yeah.
it is a frame-based system, right? So I process each frame, and there's no time dependence to earlier frames. So let's say that in magically, I have an object like, let's say, a car coming towards me.
Yeah.
It magically disappears in the next frame, and my system produces me another stuff. Then the downstream task, since it doesn't have any time dependency, tells, okay, we don't have any thread coming towards us anymore. But actually, if you look at the time and there is still a car coming towards us, and maybe in the next frame, it will just pop up back to the existence. How do you capture this type of temporal dependence?
Yeah, that's a great question. But this one is actually not only like a spatial, but it's those DV models. They are all spatial temporal. So you have information from the previous time step to make sure that you kind of exactly like you mentioned, don't have those problems. And that's actually the state of the art. Like all the baseline that we are using is something called DV former. That is actually spatial temporally, fuse those information. Yeah.
I don't have a background on the BEV.
Yeah. So yeah, each step you kind of also bring that historical information for your future. Yeah.
Okay.
Can you go back to your last photo?
Sure. Yes.
So actually I have a question for the later part, because like you are using the image features and then you use some generative AI to generate a prompt, text, and both of this will pass to the llama model and get some results. Later on, you will also using image features only pass to MLPs and try to shrink the difference between the two. I just wonder, like, under this situation, will like the model will reduce information learned from the text, because the model can be like lazy learned. We can just using the image features, because under this kind of situation, it kind of can make the loss already be small and shrink the use of the text part.
Yeah, I think that's a great question, and I will say that that's an open question because so there are two things. So if you don't do anything about it, right, like vanilla multitask, so already your performance is very low, right? I mean, you're hurting one model already. What we show that if you bring alignment, this type of alignment, at least you are not hurting the baseline model and you're improving the performance. So I will, it's hard for me to say that you are like kind of hindering it or like it's learning process, because we show that these models, like they are helping each other. They are not hurting each other by showing the metrics on both sides, not only like the detection, but also captioning, and show that there is improvement on both sides. If there is a trade-off, that's what actually we don't want to have, just like in the vanilla multitask. And yeah, so my answer on this will be that by bringing additional supervision, if we bring the proper supervision, we are not hurting it. But if we bring the wrong supervision, definitely we're gonna mess up with the learning process. So that's why we are kind of trying to strive for, bringing that guidance that we know that is correct, like ground truth guidance. Yeah.
Okay, let's thank our speaker again.
So I just have a question.
Yeah.
All of the architectures
Yeah.
which you described,
Yeah.
those are still reactive. Like the actions happen after, like the vehicle takes a reaction after an action occurs in the environment. Like first recognition happens and then it starts a planning, but not preemptive, like predicting how the vehicles are gonna perform and then create a plan around them.
Yeah. So that's a great question actually. So normally what we do here we're doing like something called open loop, right? So the other agents, they are not reacting to your changes, right?
Yeah.
But there are two ways to do this, right? So we report our results on those open loops, but if you have very good simulators, like closed loop simulator, where each one of those agents can also react to any of the chains, then you can also do those as well. We also report some of those metrics on the closed loop simulator as well, and then show that it does also still have in those, even in the closed loop simulator.
Okay.
Yeah.
Thank you.